Okay, in this lesson we're going to complete section 7.6. We're going to be looking at solving logarithmic equations. Here's the warm-ups. Again, you can go ahead and do this if you want. You can just pause the video and try to work through these. These are our exponential equations that we were working on previously, and just a review of some log properties here. I'll show the answers to it real fast. Let's review this real fast on the log properties. This subtraction right here turns into a division. We have subtraction of two logs. It becomes a division, a single log, where we have 4 divided by 2 to the third power. This 3 here becomes the exponent right up top here. So the 3 becomes the exponent 2 to the third power instead. We're going to be using that today, so I want to make sure that we're good with these log properties. Okay. Remember with exponential equations, if we had an exponential equation with the same base, we could solve this by equating the exponents. The same idea works with logs. In this case here, in this example, we have log to the same base, log base 7. So what we can do is set the insides of the log to be the same. So we could set 5x plus 3 is equal to 3x plus 7, and then we have a straightforward equation to solve. And with log equations, it's important to then plug the result that we get back into the original equation to make sure that the equation holds true. We get log base 7 of 13 is equal to log base 7 of 13, so this is our answer. X is equal to 2. So I'll just show these two examples here. You can go ahead again, practice these. I'll just pause it for 2 seconds here before I show the answer. In the first case, we go through the first step and just equate the insides of each of the two logs here. And we get an answer, x is equal to 5, and when we check that answer, we find that it's true. Now in this other case, let's see what happens here. We do the same thing. We set the inside of the natural logs to be equal to each other, and we get to x is equal to 3, but when we plug that back in, we get natural log of -1 is equal to the natural log of -1. Well, the thing is, there is no natural log of -1. So if we had natural log of -1, and let's say it's equal to x. And remember, natural log is base e. So it's saying the equivalent in exponential form is saying e to what power is equal to -1. There's no answer to this. E to the x power is always greater than 0, and so there is no solution to this. So this is an example of a case where even though we solve this equation, come down to x is equal to 3, there is no solution. So we do have to go back and check it, and we find that when we have a negative number inside of here, that's an illegal case. Second type of log equation. In this case, one side has a log, but the other side doesn't. It doesn't have, so we can't use the same method we did. But instead we could turn this into exponential form, and we take this 3 as our base, we raise it to the power of 4. So 3 to the power of 4 is equal to x plus 1. Then we can go and solve this. X plus 1, or x is equal to 81 minus 1, x is equal to 80. Here's another case. We have actually 2 logs, and we have a number all by itself. The trick here is to use the log properties. Since we have the sum of 2 logs, we want to get it down to this point where we have a single log is equal to a number, just like we had in this example up at top. So again, we use our log properties where we have the addition of 2 logs. That becomes a single log, and we multiply each of these 2 pieces here. So 2x times x minus 5. Now that we have a single log, and this log is base 10, we can convert this to exponential form. 10 to the power of 2. 10 to the power of 2 is equal to 2x squared minus 10x. So we convert this to exponential form. 10 to the power of 2, that's what we have right here, 10 to the power of 2 is equal to 2x squared minus 10x. And at this point we have a quadratic equation. We have an x squared here. So we're going to move all the terms to one side and set it equal to 0. And at the same time I'm going to divide by 2. So I divide this term by 2, this term by 2, and I bring 100 to the left-hand side, becomes minus 100 divided by 2, that equals minus 50. Now I have a quadratic equation set to 0. I could always try to factor it, or I could use the quadratic formula. In this case, it's factorable. I get x minus 10 and x plus 5 is equal to 0. And that gives me my solutions of 10 and negative 5, but I need to check these. So first of all, we plug in 10. So let's check to see if this is correct. Log of 20 plus the log of 5, is that equal to 2? I have the sum of two logs, so that becomes log of 20 times 5, 100, log of 100. And log of 100 is equal to 2, so that checks out okay. Let's try out negative 5. So we plug negative 5 into the original equation. And then we get log of negative 10 plus log of negative 10, is that equal to 2? But there is no log of negative 10. That's an illegal value. So log of negative 10 does not exist, so negative 5 is not a solution. Our only solution in this case is x is equal to 10. So that's our lesson for today. Really, we have two cases. Let's just review that quickly. We have the first case here where we have two different, we have a log on one side, a log on the other side, same base. We can just almost cancel away the log, and we have a simple linear equation to solve. And then in the other case, we have a log on one side, a number on the other side, and we convert it to exponential form to solve that. And if we have multiple logs, we can use our log properties to condense a series of log terms into a single log is equal to a number, which we then again use convert to exponential form to complete. So go ahead and try out the two problems on this last page, and here are the answers if you want to see them as well.